Welcome to the Azure AI Search, Vector Search, and Semantic Ranker Roadshow video. My name is Alexis Joseph, and I'm a Partner Solution Architect. In this video, I'll present information on Vector Search and Semantic Ranker. How does it relate to generative AI? And we'll take a look at a real-world scenario. The key takeaway is for you to finish this video with a solid understanding of how Vector Search and Semantic Ranker can assist you, how to enable it on your Azure workloads, and a high-level understanding of how it functions. First, let's take a look at the traditional approach. In the traditional approach, we have indexers that create indices with filterable, sortable, and searchable fields from raw data. Imagine turning messy documents into structured, query-ready information. Keyword search lies at the heart of Azure Search. Users input keywords and the system swiftly retrieves relevant documents. Whether it's a product catalog, legal documents, keyword search makes finding information a breeze. Azure Search goes beyond keywords. It offers cognitive skills like OCR, entity recognition, and sentiment analysis. These skills enrich documents, making them smarter and more useful. And some common use cases you'll probably see are website search, workplace search, and market search. For a more in-depth video of the traditional way of using Azure Search, I would recommend checking out this video from my colleague David on the GCast YouTube channel. So, how does Azure AI Search relate to Azure OpenAI? Generative AI models are powerful, but they have limitations. They're trained on public data up to a certain point. But what if you want to use generative AI with your own data? Enter Azure AI Search. Azure AI Search bridges that gap. It helps you retrieve information on the most relevant data for your specific use case. Whether it's documents, images, or structured information, Azure AI Search ensures that you have the right input for your generative models. Let's continue on to see how this can work, starting with an analogy, to put this all in perspective. To support search in generative AI cases, you'll commonly see vector search. You can think of it like this. Imagine you're in a library with a diverse collection of books, each containing unique insights and knowledge. Finding a book on a specific topic or theme can be time-consuming and overwhelming, especially when the content is scattered everywhere. Vector search is like a skilled librarian that helps computers quickly find and connect you to the information you need by organizing similar items close together. In this diagram, our books are the data sources. The embeddings are organization, for example, the Dewey Decimal System, and the librarian is Azure AI Search, being able to retrieve the most relevant book for you. We use retrieval augmented generation, commonly known as RAG, to effectively search for the right data based on your given prompt, take that retrieved data, and use that as context to generate a response using our generative AI models. One question you may be asking are, what exactly are embeddings, and why do we need them? Let's go over that and how they're important. An embedding is just a way to represent your text so that a computer can understand and use it. It's like a code that captures the meaning of said text. Each embedding is like a list of numbers stored in a vector, and the closer those numbers are together, the more similar other text may be. So if I have two pieces of text and they're about the same thing, their vectors should be pretty similar with their numbers. So overall, very close together in the vector semantic space. And how do we make these embeddings? We have embedding models. There are different Azure OpenAI embedding models that can create these embeddings, which are good at particular tasks. First, we have similarity embeddings, which are good at capturing semantic similarity between two or more pieces of text. We have text search embeddings, which help measure how relevant long documents are to a shorter query. We have code search embeddings, which are useful for embedding code snippets and natural language queries such as SQL. Embeddings make it easier to do machine learning on larger inputs, representing words by capturing the semantic similarities in a vector space in that numerical form. Therefore, we can use embeddings to determine if two chunks of text are semantically similar and provide a score that assesses that similarity. So we can think about it like this. In this embedding space, similar data is grouped together. We see 4 categories: cartoon, realistic, mammal, and bird. The question is then posed. Where would I, a cartoon bat, live in this embedding space? It doesn't fit any singular category. That's why vector embeddings are great at quantifying our different items, seeing how similar they are, and see the similarity in that space. Once you encode your content as embeddings, you can get them from your user input to find the most semantically similar content. For example, if the user input is what is a neuron star, you can get the embedding from that and use that to find the most semantically similar content, which will be shown as an output in your result set, which you can use to build a answer around. And then in context of a search application, often applications need to assess similarity between items. These items could be documents, sentences, images, audio, and more. While in some cases direct comparison are appropriate, so using that keyword search to find the exact word or exact phrase in a sentence, we typically want to use semantically similar results regardless of their representation, so whether it's text, images, charts, or etc. Once you have a vector encoding for your data, how do you put it to use? A common scenario is to embed all of your data into a vector database. And then when the application needs to find an item, you use a query embedding, which is basically vectorizing the input of the user to retrieve similar items and then generate an answer around them. That is the role around vector search. Now that we have taken a look at vector search, let's continue on to semantic ranking. Semantic ranking is a powerful tool that feeds in queries and results to a language understanding model. These models will scan for better matches based on context and semantics. For example, the term capital can have different meanings for finance, law, geography, and grammar. Semantic ranking detects the context to promote the most relevant results. This leads to more accurate and relevant search results. Let's see how it works. First, semantic ranking starts with a set of search results, which could be documents, articles, or any other content, like our result set found in RAG. These results are ranked based on some initial criteria such as relevance score, popularity, and recency. Next, a cross-encoder like GPT is introduced in the mix. The cross-encoder has a strong understanding of natural language and can evaluate the semantic relatedness between queries and documents. The cross-encoder is used to reevaluate the relevance of each result, considering not only the initial ranking, but the contextual meaning of the query and the content. Documents that may have been overlooked initially due to a specific domain rule or subtle nuances are now given a chance to shine. Research has shown that using hybrid approach, combining both lexicographical and vector search, along with semantic ranking, tends to generate the best results. This means by using both methods together, we can achieve more accurate and relevant search results. So let's take a look at a real-world example. We can see how vector search and semantic re-ranking can be used in a real-world scenario. Here, we have a business chat. It's able to answer business questions. It provided context. It requires information that our base model does not have knowledge on, so we have to use RAG. First, we take our documents to analyze them. The more complex files, we use document intelligence, then process it by the same tool to make the documents a bit easier to read so we can create our embeddings. Then we continue on to use Azure Data Factory to further sanitize, taking out some unnecessary data, and chunk. Chunking is a common term in RAG. It's the act of splitting content into pieces so that we can embed these pieces into vectors that will be stored and indexed in Azure AI Search. From those chunks, we use Azure OpenAI embedding models to transfer them into embeddings to be stored into an index in Azure AI Search. And how we use it? Once a user from the application asks a question, it is transformed into an embedding. Then, using vector search, we can get the most relevant information. After the result set is created, we can use semantic ranking to re-rank the results to better fit the question based on semantics and nuance. The results are then sent back to the generative AI model to generate an answer that will appear on a client application. In addition, you can use a database like CosmoDB to store the chat history that can be referenced as context if the user has further related queries. So now we can conclude with a demo of how we can actually leverage this in our Azure workspace. Let's start with a code first demo so we can see how these concepts that we talked about are applied. I'm going to take this sample from our What the Hack repository. It contains different challenges to teach you concepts in technology. We will be pulling from the OpenAI Fundamentals repository. If you would like to learn more and put into practice what you've learned, I recommend visiting microsoft.github.io/whatthehack, where you will find OpenAI Fundamentals created by our awesome team of AI partner solution architects. We will start with Challenge 3, C embeddings. We will create our embeddings from information, and in this example, we're working with automobile CSV file. This file contains different stats of cars, including their miles per gallon, cylinders, displacement, horsepower, and of course their name, as well as additional information. The goal here is to transform that data into embeddings using our text ADA model. Before starting, I created all of the Azure OpenAI models that we needed, Azure AI Search, document intelligence, and such resources. And for the sake of time, I pre-ran these code snippets. After installing all of our required packages and importing, we can store some environment variables and call those out as we make those different SDK calls. Before we get into the file, let's take a look at this small text example here. So here we have an input of, I would like to order pizza, and we have an embedding variable. We can use this function called getEmbedding, where we can take our input into our embedding model and then see the results here in our vector. And now we can actually use this with our data. So now we can see our automobile CSV and the information it contains. It contains a shortened list that we can observe where we have our name, miles per gallon, and other additional data with a total of 398 rows. And we can just see an abbreviated version here. And what we can actually do here is actually see how many tokens does it take for our names to be processed. So here we have tick token and we have the get encoding 3L 100K base. And you can see here we're doing a loop where we're actually taking the amount of tokens and defining it in that chart here. So now we can see the amount of tokens it takes per each name to be encoded. If we continue further, we can actually see some code here where we can split apart a word to see how many tokens it would take, but also how it would be split apart by bytes. So we can see here the name of our first car and how it's split into 6 different tokens like we counted above. So now we have this code here where we can actually get our embeddings per name of each car. So we have this code that runs this loop where we call get embeddings for each X, which is each name. And then we can see here in this chart where we have our first our tokens, and then we can see the result vector of splitting apart these names. So now we completed that, we have kind of seen how we can create some embeddings and view the amount of tokens it can cost for text. Let's continue on to RAG and how we will actually use this in a situation for search. Continuing on with challenge 4B, retrieval augmented generation for unstructured data, we're actually going to use some data that revolves around prompt engineering and other NLP concepts. And these are all in PDF files. So we have to extract that information and make it understandable for our different models. So here you can see we're importing everything that we do need. We're importing additional fields for Azure Search so we can better organize all of our data as well as extract the data from these PDF files. And of course, same here, we have our definition of all of our API keys and everything that we do need to actually call these SDKs and models. Here we have 2 folders. One is for our raw data, which is basically all of our PDFs unaltered, and then we have extracted data. So this is our data after going through document intelligence and extracting all of the important information. So here we're using forms recognizer, but that is the same thing as document intelligence, just renamed. So we're having a client here, we're defining the endpoint, and then further on, we have some helper functions that help go through all of that information that the document intelligence was able to uncover, going page by page, uncovering that information and recording different results such as the page numbers, where this page came from, what file name, and the content that's actually on the page. So we see here after running those helper functions and getting extract files, so putting our raw data folder in and extracting it, we have our process files, which will be all the file names and the written output, and then it will contain all of the content, which you can see here after we ran that function. So we can see all of the extracted files. So as we walk through, we'll see how exactly this data is split. We have the document ID as well as the document name, file path, the page number, and the actual text that's within it. So if we go through our documents and we say index one, we can see the page number and the additional information there. So what we can do here after having all of our information, we can create an index in Azure AI Search. So right now we created an index called Research Paper Index, and now we're creating that client so we can actually interact with it. So here you can see the successful build of that said client. And then from here, we're able to actually create fields that help organize our data better within that index. So you can see here we have it organized by document ID, page number, file path, document name, as well as text. And we're defining that my semantic configuration. And now you see we successfully created that index. And now that we have created all of our information that we needed to upload in that index, we can upload it safely using our endpoint. And you can see here we successfully did that. With all of the files successfully uploaded, we can now start to ask questions. Let's check out this first query here, where we limit it to the first 10 different results. So here we're asking, what is automated prompt engineering? We're able to send that to our Azure Search client and receive that in this different data frame once we define that. So now we can see 0 to 9, we have different chunks that are useful to us. And now that we have these chunks, we can continue on to embedding. So we're just going to use some helper functions that help us best complete these embeddings. Again, using that text embedding ADA model first, and then we have a helper function to actually have this completion. So we're using GPT-3.5 Turbo. So first, we're taking the actual embeddings, we're applying that, and you can see all of these here where it's running those embeddings, but also we have similarity. So this is going to be our similarity point towards our actual query and how they match up and align to what we asked initially. And based off of those similarities, we're actually going to grab the top 3 results and use that to generate an answer. So now we have our prompt here where we're providing a query, we're taking the user's query, and we're extracting the relevant pages. So if we go all the way down to the bottom, we can have our get completion and with our response. So it's talking about automated prompt engineering refers to the process of automatically generating and selecting instructions and some more text. If we continue further down, we have a couple helper functions here, query search, which we can call that search client that we called earlier to grab the top whatever results that we want. The default is 10, but we can also redefine it in our function call. Then after getting those results, we can embed those chunks so we can get the semantic meaning and the embedding for it. And then as we continue, we can get the similarity score and drop that in. So now we have the prompt here. We take that user's query and then we can take the list of extracted pages. So we have all of the information that we need to answer the user's query. And when we drop these results for the references for the resources, we're going to try and get the top 3 results. Again, using those top 3 results, we're actually able to bring them in for get completion, adding that additional context so we can generate an answer around it. So if we continue further, we can actually see how this function is used. How does automated prompt engineering work? Where we're asking for the top 5 results that our AI search client was able to grab. And then again, we're using embeddings. And then based off of the similarity search score, we're able to grab the top 3 to generate this answer to have references on. So here we can see this information is based off of fact from that PDF. And if we continue on, we have another query of what is prompt tuning. And again, we're taking those top 3 results that were embedded and we're printing an answer here. So with that, that concludes this part of the code first track. We were able to retrieve, we were able to embed, and we were overall able to generate some answers that are based in fact and grounded. So right now I'm in the Azure portal in my Azure AI Search resource. If you would like to automate a lot of the processes that we just done in code, there's actually some cool features here. So you can actually import and vectorize your data as long as you put it in a storage account. So I have an example here where some news articles in a CSV folder. And now what we can do here is actually call our Azure OpenAI resource, and it helps you create that there if you haven't made one, as well as an embedding model to use. And of course, it's going to cost you embed your models. And what's actually a cool feature here, if you need to use document intelligence for your data or your unstructured files, you can call it from here to enrich with AI skills. You also have to have an AI service uploaded and created. And then, of course, you can enable semantic ranker to help you get some better results there, semantically being understood. And once all of that is completed, you can rename your index and then run your indexer. But for the sake of time, I went ahead and did that already. So we can go to our indices. I created an index here named news index using the feature that I just showed. And when you first see it, you're not going to see anything until you put something in the search. So after I put that star, that's just going to list out all of the different chunks that we do have in this index with the actual vector embeddings. So now you can see that is ran through. We have our chunk ID, parent ID, as well as the title and the actual content that is within the chunk. And all of these different parameters that we'll use for different similarity searches and just being able to query our data. So I can actually go up here and ask something like, give me a positive read. And it's actually able to give me a article that is about something positive. We can see the chunks here as well as additional information here. So this is going to give us some top contenders when it comes to that information. Now we can continue on to Azure AI Studio. So this is great if you want to do a more custom model and you want to do some evaluation and additional testing as you work with it. This is a great way to create your initial index so you can use it for search. So if you create a Azure AI resource, you're able to actually create a project and further on reach this page. You can go into indexes and create your own using your different data. And for the sake of time, what I did here was actually use some additional CNN data to actually run this flow. So you can actually use this in prompt flow as well. This takes that kind of directly from it, where you're able to create your chunks from your data, update, and then register your index. And we can actually interface with that data that we just entered in our search instance by going to our playground and actually working with a model with this. So we can go over here to adding our data and we can choose through different search types. I personally have my CNN daily index that I just created through that flow. And go ahead and change my deployment to this GPT 3.5 Turbo 16K. And then let's start chatting. So this has a lot of data on different news articles around the world. So I'm going to ask something about London. Let's say, give me some news about London. And now we have some highlighted documents here with some references listed. So we can hear about this underground fire, some protest, and more information there. And now we can see our references here, how it references that Excel file that we put into that index while we were filtering and processing it. To conclude, you can leverage vector search and semantic ranker to ground your generative AI models to generate some content that is based on facts. To continue to learn, I recommend completing that What the Heck that I demoed, as well as leveraging resources such as MS Learn and the additional videos that will come out in this series. Thank you for watching, and I hope you enjoyed this video.